Hello, my people. I hope we're doing well. This is video number 3 for double angle identities, and we'll be doing some of the equations, solving of equations. And on this first batch, it'll be 0 to 2 pi, and on the last two, it'll be negative infinity to infinity. So let's go ahead and get started. Now, we're not dealing with a verification problem. We're dealing with an equation, so we can actually bring this over to the other side. And now we need to figure out a way to transform this. Well, that winds up being one of the simplest ones, which is, of course, why we're starting with it. And you change sine 2x into 2 sine x cosine x, at which point you recognize the fact that you have a GCF, and you set cosine x equal to 0, and you set 2 sine x minus 1 equal to 0. And where is cosine x equal to 0? Well, cosine x is equal to 0 on 0 to 2 pi at pi over 2 and 3 pi over 2. Sine x is positive 1/2 at pi over 6 and 5 pi over 6. And there you go. Okay, this next one, I see the fact that I have a quadratic. It's in terms of cosine squared. I see I have a second term in terms of sine, and I have a last term in terms of cosine 2 theta. Now, all of this tells me that I'm going to be using sine theta for my ultimate equation, and the reason is this one right here can't be changed, whereas this one and this one have the possibility of winding up solely in terms of sine. So what I'm going to do is I'm going to transform cosine squared into 1 minus sine squared. Leave this as sine theta, and I'm going to transform cosine 2 theta into 1 minus 2 sine squared theta. And that winds up giving me everything just in terms of sine theta. Let's go ahead and distribute. And I'm going to bring the 1 over here, and now I'm just going to collect like terms. Okay, this is second degree, that's second degree, so I'm going to get 2 sine squared theta. That's the only first degree term, so that's going to be 3 sine theta. That's positive 2, that's negative 2, so those cancel out, and I'm just left with minus 1. Now, the question is, does this factor? Well, you can always do your, b squared minus 4ac, and that's going to be 9 plus 8, or 17. It doesn't factor, okay? You could use the quadratic formula, or you could complete the square. It really doesn't matter. Let's go ahead and complete the square. I think that's probably going to be... we just don't do it enough. It's probably going to be annoying because we have to deal with this fraction right here. But fractions, you should be able to deal with them. Now, in order to get this right here to complete the square, we need a leading coefficient of 1. That's why we divided by 2. And then we need to take half of that. Well, half of 3/2 is 3/4. 3/4 squared is 9/16. But if I add 9/16 to this side, I have to add 9/16 to this side. And therefore, this factors into sine theta plus 3/4 squared is equal to, well, that's 8/16, and that's 9/16. That's going to be 17/16. There's that 17, right? So what I'm going to do here is I'm going to get sine theta plus 3/4 is equal to plus or minus root 17 over 4. And we get two possibilities. We get sine theta is equal to 3 plus root 17 over 4. Well, 3 plus root 17 over 4 gives me a value that is not in sine's range. or sine theta is equal to 3 minus root 17 over 4. And at that point, I need to consult my calculator. Okie dokie. Let's do the 3 minus root 17, and then divided by 4. And then we're going to take the arc sine of that value, and we're going to get theta is equal to, right, negative 0.285. Well, first of all, I know that sine is only going to give me one of those answers, whereas I need two of them, okay? But this tells me that the first one that I'm looking for is in the fourth quadrant. So in order to find this one in the fourth quadrant, I simply need to deal with its coterminal, which is 5.999. But in order to get the other one, okay, I need to figure out, basically this right here is negative, this one is 0.285 in the negative direction, so 0.285 below the x-axis. The corresponding one in the third quadrant will also be 0.285 below the x-axis. So what I need is I need to take this value right here, okay, and I need to basically do pi minus that value, because what I really need is pi plus the absolute value of that, because it's going to be just past, pi, right? And so I get 3.426, and those are my two values that are on 0 to 2 pi. And I could have done it by quadratic formula. It doesn't really matter. We would have gotten to the 3 plus or minus root 17 over 4 in fewer steps, but we also open ourselves up for possible, mistakes. And it's always good to review our completing the square because, I actually prefer it. Alrighty, let's go ahead and take a look at this next one. We're still on 0 to 2 pi. We're going to do the same thing with this one that we did with sine 2x is equal to cosine x. We're going to go ahead and bring this cosine x over to this side. Now, I need to figure out which one of the three identities for cosine 2x I'm going to use. It does me no good to introduce sine into this equation when this is cosine right here. So if I can avoid using sine, I'm going to, which means I'm going to have 2 cosine squared x minus 1 minus cosine x is equal to 0. Now, of course that comes from cosine 2x. I'm going to take down the parentheses and I'm going to reorder in descending order. And now I can factor. Now, 2 is prime, so the only choices are 2 and 1, okay? 1 is prime, so it's 1 and 1. So if this factors, I need one of these to be positive and one of these to be negative. Well, this is negative, so obviously the product that includes the 2 cosine x is going to be the negative 1, and then there you go. So this gives me cosine x is equal to negative 1/2, and this gives me cosine x is equal to 1. Cosine x is equal to negative 1/2 at 2 pi over 3 and 4 pi over 3, and cosine x is equal to 1 at 0. Now the only thing that is new in this section is basically this portion right here, okay? It's a different identity, but the strategy remains the same, okay? Now this one is similar to the one on the previous page. We're going to use this middle term, the one that doesn't change or can't change, to determine which trig function we want to try to turn everything else into. Well, that's sine. So in this one, we actually don't have to use Pythagorean. We can just leave that one as sine squared. This one, however, needs to change, and it needs to be changed using the cosine, the double angle cosine identity that actually is 1 minus 2 sine squared theta. And when I basically break down those parentheses, which I can do without doing anything because there's a positive out in front of here, so those are really just kind of window dressing, I get 3 sine squared theta minus 4 sine theta plus 1. Okay, well, let's see whether that factors. If it factors, then my b squared minus 4ac will be a perfect square, right? B squared minus 4ac. 16 minus 12 is 4. 4 is a perfect square. This factors. Thankfully, both my leading coefficient and my constant value are prime, and so there's not much of a mystery in how it factors. Both of these are negative, and when I double check by foiling this in my head, I do wind up with 3 sine squared minus 4 sine plus 1. This gives me sine theta is equal to 1/3. Gonna need my calculator for that one. And this gives me sine theta is equal to 1. Don't need my calculator for that one. That is pi over 2. Now, let's go ahead and consult our trusty calculator for the sine, arc sine of 1/3. Okay. So we're going to do the arc sine of 1/3. That's going to give me theta is approximately 0.340. And on the AP exam, you can either round to 3 decimal places or truncate, which just means chop off. So it could be 0.340 or 0.339. It doesn't really matter. And then, of course, I need the supplement for this, which winds up being 2.802. So those are my 3 values, which are solutions for that trigonometric equation. Now, of course, one of them being a unit circle value, 2 of them being calculator generated. All right, let's go ahead and take a look at this one. Notice that when we get here, our interval has changed. We're at -infinity to infinity. So that's going to be, you know, plus pi n, plus 2 pi n, all that sort of fun stuff. Now, what we have here is we have a double angle and we have a quadratic. We don't have a quote-unquote linear term, like a first degree cosine term with just a theta. So I actually could change both of them, but why would I want to, right? If this is already in terms of cosine squared and there exists no reason for us to change it, then let's just go ahead and turn this one into cosine squared by substituting in 2 cosine squared theta minus 1 as the double angle identity. And that is going to allow us to basically turn it into 6 cosine squared theta. That's going to be minus 3. And so cosine squared theta minus 3 plus 2. These 2 are like terms. These 2 are like terms. I'm going to get 2 cosine squared theta minus 1 is equal to 0. Now, you can either go ahead and set that and solve that. You just have to remember the plus or minus. If you're one of the people that forgets the plus or minus, then you can force factor this one into something like this. This is going to give us cosine theta is equal to -1/√2, which you should know by now is your unit circle value of -√2/2. This one is going to become cosine theta is equal to +1/√2. And so between the 2 of these, basically what you have is every value that has a reference angle of pi over 4. Because this is going to give you pi over 4 plus 2 pi n and 7 pi over 4 plus 2 pi n. This is going to give you 3 pi over 4 plus 2 pi n and 5 pi over 4 plus 2 pi n. That is all 4 of the pi over 4 reference angles and every coterminal after that, which can of course be summarized very succinctly as theta is equal to pi over 4 plus pi over 2n, because you add pi over 2, it's going to get you to 3 pi over 4. Add pi over 2, it's going to get you to 5 pi over 4, and then to 7 pi over 4, and then to 9 pi over 4, and then to and on and on and on and on and on. Okay. All right, let's go ahead and take a look at this last one right here. Did I say last one? Yes, I said last one. Aren't you thrilled? Notice that we are still on negative infinity to infinity, so we are going to be dealing with the, plus pi n, plus 2 pi n, all that sort of fun stuff. Now, what I need to do is, this is in terms of tangent, this is in terms of sine, but tangent has sine inside of it, so really the emergency is to get rid of that right there. So that becomes 2 sine theta cosine theta, and the 3 just sort of comes along for the ride, and that is equal to sine theta over cosine theta. Now, you don't have to do it this way, but I find that most people kind of jive with this. If I do it like this, then I can sort of quote-unquote cross-multiply, right? And I get 6 sine theta cosine squared theta is equal to sine theta, and then I can basically subtract it from both sides. And then I can factor out my GCF. Now this one is going to be really easy. That sine theta is equal to 0. This one is going to be cosine squared theta is equal to 1/6. Or, if you want to go ahead and get ahead of it, call it 6 over 36, because when I take the square root, I'm going to get plus or minus root 6 over 6. Now, the great thing is that whether it's positive or whether it's negative, this describes 4 angles on the unit circle, all of which have the same reference angle. They have the same reference angle because they have the same adjacent over hypotenuse ratio, right? And so you really only have to find one, and then you can sort of extrapolate from there, which is nice. That means we only have to use our calculator once. Okay, so let's go ahead and do root 6 divided by 6, and then let's go ahead and do our arc cosine of that, and our first value is going to be 1.150. Now that means that if we think about it in terms of the unit circle, right, this is 1.5, it's kind of up here, and that is, right there is 1.150 radians. But I also need this one, and this one, but they all have that same reference angle, so you just have to relate them to pi and 2 pi. This one is 1.15 shy, okay, of pi, so it's pi minus that answer, okay? Then you have one that's 1.150 beyond pi, so it's pi plus that answer. And then you have one that's 1.150 shy of 2 pi. But the great thing is that this one, and like the ones that are along here, are exactly opposite each other on the unit circle. So you can actually, you don't have to deal with the 4.291. You can just call this plus pi n, and you're golden. You just have to figure out these as well. Well, you've already gotten the 1.991, and so we'll just do the plus pi n on that one as well. And so you get those 4 answers, and of course sine is equal to 0 at 0 plus pi n. Now this using the opposite to reduce it down to plus pi n only works when you're taking the square root and you get the plus or minus, right? Because the positive ones, cosine theta is equal to positive root 6 over 6 is those two, right? And so if you just have the positive, you can't use the plus pi n because they're not pi apart, right? And then, of course, cosine theta is equal to negative root 6 over 6 would be those 2 angles, and they're not pi apart. But when you have both of them, you do have the fact that this 1.150 and this 1.150 plus pi are, of course, pi apart. All right. I hope that that helps. We will be doing sort of mixed review on sum and difference identities and double angle tomorrow, as well as on tomorrow's homework. So I'm hoping that that will sort of iron out any residual questions. But I'm hoping that the logic that you've sort of become comfortable with when we are doing fundamental IDs is already firm, and all you're having to do is just lay new IDs on top of that understanding. So there really shouldn't be any discomfort. It's just kind of the annoyance of having a new set of identities. But they are kind of neat, and they are really, really helpful a whole lot, which is why I'm asking you to learn these. The ones that aren't really all that helpful, I haven't asked you to memorize. If you have any questions, please do shoot me an email or send me a message on Teams. Bye.